Hey students, I thought I would add a little supplement to the lecture. We had only enough time really to go through the theory behind it and the ideas and not really any examples to kind of show you. And so I thought I would try a few. I made quite a big list because it's a big chapter. I'll start with number 1. It says here, common static electricity involves charges ranging from nanocoulombs to microcoulombs. How many electrons are needed to form, and I'll say Q equaling negative 2.00 nanocoulombs? All right, so obviously the nano part of this means 10 to the minus 9, or at least I hope you know that. The other thing is clearly there is a negative sign, and that's good too because, whoops, negative 9. Negative 9, getting ahead of myself. 19 is going to be the charge of the electron. But, excuse me, but that is then this fact that you put a bunch of electrons together, they're negative. So I would describe it this way, that one electron has a charge of negative 1.602 times 10 to the minus 19 coulombs. And then you would double that if you had 2 or triple that. But let's say you have n electrons, and then that total is supposed to equal to a negative 2.00 times 10 to the minus 9 coulombs. So then we can solve for n. And so grabbing a calculator here, we've got, and I'll just cancel the negatives in my head. So we'll go 2 times 10 to the negative 9, and then divide that by 1.602 times 10 to the negative 19. And so this comes out to be 1.2, I'll go up to 5, times 10 to the 10th. And so that's how many electrons in that. Now, part B says, so this is A, part B then says how many electrons must be removed from a neutral object to leave a net charge of 0.5 microcoulombs. So again, same logic, we would go n times the charge of one electron, and that's supposed to equal what I'll call Q, the total charge. And so just like in A. Now, in this case, we're removing them, so I don't know if you want to do absolute values or put a sign convention here. But the total charge, they say, is 0.5 microcoulombs. And so micro is 10 to the minus 6. And then again, we've got n, and we've got the charge of negative 1.602 times 10 to the minus 19 coulombs. So in this case, I guess we can interpret the negative as mean n is how many you have to take away. Because when we do the math here, we're going to get a negative, and we're going to have a 0.5 times 10 to the negative 6. And then we can divide that by our negative 1.602 times 10 to the negative 19. And so, not a surprise that it is many, many more, because we are talking about charges that are a total of, well, that's nano, this is micro, but it's point micro, so this is 100 times, and so 100 times would also be part of the number. So we need to remove 100 times more here. So this is about 3 trillion, and then this looks like, if we call it a 12.5 billion electrons that have to be removed. All right, hope that one is somewhat helpful there. Here. Okay, let's try number 10. Let's see what 10 says. 10 says, what is the repulsive force between two pith balls that are 8 centimeters apart and have equal charges of a negative 30 nanocoulombs? So Coulomb's law says the magnitude of the force is Coulomb's constant times the magnitude of the first charge times the magnitude of the second charge divided by the square of the distance. So this is a pretty much plug and play, if you will, plug and chug on this one. But it's 9 times 10 to the 9th. The only thing I want to caution you about here at the beginning is that we need to watch our units. And Coulomb's constant means that we need distance in meters and charge in coulombs. So when they say 30 nano, I need to switch that 30 into, or the nano, into 10 to the minus 9. So that would be the charge. And they're equal, so I'll just save myself a little writing and put square. And then same idea with the distance. It needs to be, as we can see, in meters, and they gave it to me in centimeters. So I'm going to convert it to meters before I put it into my equation. And that way the square meters will cancel, and also the square coulombs will cancel, and you'll be left with the magnitude of the repulsion force. And depending on how you lay them out, one will be left and right, or one will be up and down. You know, it doesn't really matter. They don't really know. They just say what's the repulsive force. But I'm pretty sure they're talking about the magnitude, because one is left and one is right. So we can't really answer that. Or one is up and one is down. Or if they could be even at a 45-degree angle. All right, so putting in my numbers, I would say this is 9 times 10 to the 9th, and then times 30 nanocoulombs squared, then divided by 0.08 squared for the distance. And we're looking here at, I felt like I hit something wrong. 30 nano squared, 9 times 10, 9. Okay. And so this is a force of 0.001, well, let's call it 27, or 1.27 times 10 to the minus 3. And I think that's good. Let's see, this minus 9 would cancel with that 9. So then we would have a 10 to the minus 9. That would drop at 10 to the minus 8, 10 to the minus 7, and then minus 5, minus 3. Okay, good. So I kind of suspected it was a little bigger than that. All right, but let's try another one here. They get a little harder. Number 25. And what does 25 say? Let me scroll down here. 25 says, point charges of 5 microcoulombs and negative 3 microcoulombs are placed 0.25 meters apart. Where can a third charge be placed so that the net force is 0? And then B, what if both charges are positive? All right, so they say they're a certain distance apart. They don't say which one's on the left, which one's the right. They don't say if it's up or down. So we have, I guess, a little bit of leadway here. And so I'm going to go ahead and put a 5 first, since they listed it first. And I'll just go left to right like I was reading. And then negative 3 microcoulombs here. All right, and then, of course, it says, where can a third one be placed so that the net force is 0? Well, I hope you kind of see that if you were placing a positive charge, or any charge, in a position that is above the line connecting to them, or if you drew them vertically, you know, left or right, maybe I'll kind of imagine a positive right here, that would be pushed away, and this would be attracted down. So right there, I can see that they're both kind of left and right, although there is an up and a down. And of course, the left and right is never going to cancel off. So these both are towards the left, excuse me, the right, and it just won't cancel off. On the other hand, if I were to put it down here, that looks like I would have something that would be, pushed away here and attracted here. But I'm going to say it's really kind of the same piece. In fact, what I really wanted to say about this problem was then let's stop looking at the force. And so I've been drawing little arrowheads that you might say represent the force. Let's draw the electric field. That's a little more advanced, but the electric field then, and I'll put a little equation, the force on the third one would be the charge of the third one times the electric field created by, and I'll go 1, 2, meaning the field from 1 and 2. So what I'm getting at, and not really much different than looking at the force, is I need to find a place where the field comes out to be 0 from these two, because then I would have 0 times any charge. And that's why I kind of said, let's abandon this, because I looked at positive, and then you would start arguing, well, what about the negative? And hopefully you're beginning to see that regardless of what charge you were to put, if the field is 0, then a positive or a negative multiplied by it also comes out to be 0. So I think it is wise to look not at forces for this problem, but to look at the field. And so maybe to make the field stand out, I'll change colors. And again, if this is the 5 and this is the 3, I would have something that maybe looks radially outward from this one, and something that looks radially inward from this one. I should have watched my ratios. 1, 2, 3, 4, 5, 6, 7, 8. I should have drawn like 5 or 10 here. So then I could draw like 10 here and 6 here. But let's not worry about the number of arrowheads to indicate its strength for just a second. Let's just see, where do you think you could possibly get, kind of imagining these vectors and these vectors, but they have to add up to be 0. And see, the only way two vectors add up to be 0 if they are equal in magnitude and opposite in direction. And that's crucial, because anything, if I draw a line connecting them, and as we started to see at the beginning here of 25, anything that's not along this line could never be completely opposite. So, something, say, here is going to have the electric field coming from the 5 like this, and pointing this way for the 3. And so we can then kind of expand a more generalized statement. I was just kind of doing it between the two and plus only, but we could expand that thinking to anything below this line would never be completely opposite. And likewise, anything above this line would never be completely opposite. And so the first part of my thinking is, okay, this could not happen except along the line connecting them. And in fact, if you look at the line connecting them but between them two, it can't happen there, because even though they're in the same line, they're not opposite in direction. They're in the same direction. And it kind of makes sense. If you were to put, say, a positive there, it would be pushed away from this positive and attracted to that negative. And so it would go to the right. And a negative at this would go to the left. And that would be the same logic all the way along here. So, again, couldn't be below the line, couldn't be above the line, couldn't be in the line segment connecting the two. But what about the line segment, or this, I guess, would be a ray segment, going off to the left or going off to the right? And so maybe I'll just, let's see, black or something, put a little dot here. What about there or here? See, the field from the 5 is pointing to the left, and the field from the 3 is pointing to the right. So there, they are in opposite directions. And in fact, over here, the same thing, they're in opposite directions. The field coming from this number 3 is to the left, it's pointing towards the negative, and the field over here is pointing to the right. So here, along these ray segments going out, we have the potential of the 0, because again, they have to be equal in magnitude, opposite in direction. And these are the only places they can be opposite in direction. So let's look at that other criteria, which was they have to be in the same magnitude. Which then when we give this some thought for this left-handed one, we can rule it out. Because notice that any point over here is closer to the 5 than to the 3. And the equation for the electric field depended on both the charge and the distance. And so over here, points along this ray segment would have a bigger charge that is closer to it than this other one. And therefore, even though the field from the 5 and the field from the 3 are opposite in direction, they're never going to be of equal magnitude. So finally, I can narrow it down to this spot, where the field from the 3 pointing to the left is closer than the 5, and that field is pointing to the right. And that field then would be stronger for one factor because it's a bigger charge, a 5 compared to a 3, but it's also further away. And there it is. And that's how we're going to balance it. So it's somewhere along here that the condition that the two vectors are equal in magnitude but opposite in direction. So it's only out here somewhere. Everything else we can eliminate. So now it's just a matter of kind of plug and chug in here. And so why don't we call this distance from the 3 to where we're going to put the third one, or where that question is, how was it phrased? Where can a third one be placed? I'll call that x. So the net force is 0. So x is along the line joining the 3 and the 5, and it is also measured out from the number 3. And in my case, that's to the right. But I don't want to say the right because you might have drawn these the other way. You even might have drawn them vertically. But here's what it's going to say. So electric field total is going to equal to what? I'm going to say the field over here from number 3 is in the negative direction, and it's Coulomb constant times the 3, and what units were these? Micro coulombs. We'll debate if we need to switch to coulombs here. And then a distance of, and I'm just going to call it x squared. So that's the electric field from the number 3. Notice the negative because it would be pointing in the negative direction, which is in where I have it. It's, this is the field from number 3 is in the negative direction. So then I'm going to add to this the field from this one, which this field over here would be in the positive direction, so also positive. It'll be Coulomb's constant. It'll be 5 microcoulombs, and again, we can have a discussion about whether they should be in microcoulombs or coulombs in a second. But the distance here would be further. It would be not only the x, but it would be x plus, and then we come back to the problem. Looks like 1/4 of a meter is this extra separational distance. And of course, the goal is to get that equal to 0, because if the field is 0, then multiply that by whatever charge you put there. You could put a lot, you could put a little, you could put positive, you could put negative. It's just going to come out to be 0. which is really very nice because you can factor out a K and divide it, so it goes away. You could even factor out the microcoulombs and divide by it. So that's going to go away. Then you're left with a negative 3x squared, which when I move to the other side becomes plus 3 over x squared. And then this one is the 5, again without the microcoulombs, and then this would be x plus a quarter squared. And of course now we have a tough problem. We have a quadratic equation. And now we've got to just solve this for x. So why don't I do something like this? I'll move the x squared over. And then I'll move the 5 down and over. Maybe I'll take the square root. Oops. Square root. When you take the square root of a fraction, you take the square root of the numerator and the square root of the denominator. So this would actually be 3 divided by 5. And then the square root of that would be 0.775. And now we can solve for x. So I'll put x equals, and when we bring this over, we can do the distributive. So the 0.775 times the x plus this point. Looks like I put my decimal in the wrong place. Why'd I do that? Right, that's supposed to be right there, a quarter. Let me check the wording here. Yeah, it's a quarter of a meter. Yeah. Okay. So leaving that x alone, but bringing this to the other side, gives me my 0.775 times x, so that's that first term, and then times the 0.25. And so that's a 19.4. If we bring this over to here, we've got 1 minus point. Yeah, let's do 775. I was just thinking maybe we needed the quadratic here, because there is this plus minus issue that we should probably talk about. But let me go with the plus here at the beginning. So taking a 1 and subtracting this gives me a 0.225. And of course then the 0.194, guess there's an x. And so solve this for x, 0.194 divided by 0.225, and we're looking at 0.862 for the x. Good. Now, like I said, if we looked at the negative sign, then we would bring it over here. We would then get a negative x, and I guess in our picture what that would mean is we would be over here somewhere, and we would have solved where the two fields are equal. The problem, though, is in this area, they can be equal, but they're not opposite in directions. So not a surprise that the math would give us two answers, because our math is just saying when is the magnitude of the fields equal, not when does it, be equal and opposite. So in other words, I didn't really need to focus on the negative when I took this square root, but it was probably kind of important that I don't cheat the math and say, oh, I can't just throw it away. I got to kind of justify what it means and why I can then kind of ignore it. And so that's what I ultimately did. So I finally did ignore it. Oh, and I guess my units here are meters. All right, so that was a little harder one, and that was a good one, and it got us into a little deeper idea of electric fields, and that's the harder part of this chapter, the more advanced, if you will. All right, so let's move on to, I think we'll get harder here. It says, what is the magnitude and the direction? What is the magnitude and the direction of the electric field that exerts a 2.00 times 10 to the 5 newtons upward on a negative 1.75 microcoulomb charge? Okay, so this one is saying that if you're looking for a force on number 2, you have to then take the charge of number 2 and then multiply it by whatever the electric field is, wherever it's coming from. And so it's coming from other charges. But what we have here are vectors. And so here's something kind of nice to say here. This says what's the magnitude and the direction of the electric field that exerts an upward force. So we mentioned in class that the upward field, and therefore the upward force, would be the direction that a positive would move, okay? And the negative would be the opposite. So if I were to say the electric field was up, then a positive would be pushed up, but a negative would be pulled down. That's really what I'm getting at. And they make it very clear that what we have, and I'll just read it again. It says, what is the magnitude, and here it is, the direction of the electric field that exerts an upward force, but it's on a negative charge. So I'm going to redraw my grid here and say then the field must be downward or in the negative direction, because then when you put a charge of Q2 in there, you would calculate its magnitude of the force as Q times the electric field. But what you're going to be getting here when you think about these as vectors is with this negative right here, they're going to be opposite in direction. And so the direction of the force and the direction of the field is opposite. And that's why I picked this one, is so I could have this little discussion. And that's what they're trying to point out here, not so much the math in number 27. It says, what is the magnitude and the direction of the electric field? Okay, that exerts this many newtons on a killer well. I mean, not killer well. That's the next set of problems. Sorry, on this charge. And so here, I guess I would say then that I've answered the first part, and that is the field must be down, well, back to here, so that the force is up. And so let me just take a moment to say again that right here, the field and the force are in opposite directions according to this math. For the negative, because you'd put a negative. But if you put a positive here, they're in the same directions. And that's an important concept. And like I said, why the author wanted you to put here, it says, what is the magnitude and the direction of the electric field? So I can put here for direction, I can say field is down, because that's how we're going to get an upward force. Then when it comes to magnitude, I can just say, well, the magnitude of E is the magnitude of F divided by the charge that you're going to place there. And we can even just do magnitude of that. So the magnitude of the force is 2 times 10 to the 5 newtons. And the charge that they're placing there is the negative, I won't put the negative, but 1.75 times 10 to the minus 6 coulombs. And so grabbing my calculator, I can go 2 times 10 to the 5 and divide that by 1.75 times 10 to the negative 6. And I get 1.14 times 10 to the 11 newtons per coulomb. Okay? And so keep in mind that they want you to also see that the units for the electric field are newtons per coulomb. And of course, they are huge. They sound big, 10 to the 11th, and rightfully so. But there is, oh wait. Wait, maybe this goes back a little earlier here. Hang on. Because I just noticed the printed version. Yeah. Okay. So my old printer version has a +5. I think that's a typo, because the newer online version has a -5 there. So that would change that by a 10, so that'd be a 1, and so this would be 11.4 newtons per coulomb. Okay. Okay, so yeah, I should stop looking at this printed one. This is not the first time it got me into trouble. And it makes me want to jump backwards a little bit, because there was another one that I was bothered by the size, because when I'd originally read it, I was bothered here, and it was number 10. So let me go to the PDF and say, what is the repulsive force? No. Okay. Okay, that wasn't the issue on number 10. But it's definitely the issue here on this one. So if you guys have the newest PDF version, you'll probably have a -5. I'm pretty sure mine is the most current PDF version. Yeah. But let me just double check, because now I am really bothered by that. But yep, they got a 10 to the -5. And then let me look back over at my printed one. Yes, I think there's a little typo problem going back and forth. But I'm going to use the newest one. So that would be the right answer for 27. Okay. So let's try another one here, number 37. And let me stick to the PDF here. This one says, sketch the electric field in the vicinity of this conductor. And so they give a conductor that's kind of this long cylinder shape, I think. The way they do the lighting makes it look like it's a kind of a hot dog shape here. So it says, sketch the electric field in the vicinity of the conductor, given that the field was originally uniform. All right. So if I make a uniform electric field, and let me not modify it quite yet, but you put a conductor in here, remember, charges will shift around, and the total field then will be the original field plus the field that's created by this shifting charges. And this gives me a chance to point out a couple of important things about the conductors. And one of them was that the electric fields would be perpendicular to the surface. So what's going to ultimately happen is charges are going to shift around so that the field will always be perpendicular to the surface. 2, we learned that the electric field inside the conductor has to be 0. And 3, we learned that more of the charge is where you have the smallest radius of curvature, or the largest curvature, if you want to do that. But the smallest radius of curvature is probably the best way to describe it. So let me draw this hot dog shape again. and just say that way above the hot dog or way below the hot dog, the field is probably unaffected. So I'll just draw two straight lines. And right where the hot dog is, I guess the field would come in and then would terminate, because what it would do is it would draw negatives over here, leaving a positive here, which then would start up the field again. So this is why we would say there is no field inside this hot dog shape. Okay. Now, I guess the other thing I would probably do is above and below, they probably have identical symmetry. And since the field has to be modified and hit it perpendicular, and the majority of the charge has to be where the radius of curvature is small, I'm kind of thinking something like this might happen. And of course, identical on the other end of the hot dog. And it would be reinitiated. And then eventually get far from those charges, so be back to what it originally was. And maybe further along on this hot dog shape, there would be less charges. And making it identical top and bottom might look something like this. Okay. And then finally, maybe one more step, and that is if I can squeeze one more in here, maybe the field gets adjusted to kind of match the overall adjustments, but not adjusted so much that it actually then terminates, actually turns and hits there. And so this would be my thinking of, okay, what would the electric field look like? And so that's an important part of this chapter, is to try to get that gut feeling of, okay, what would this electric field look like, and why? Mm-hmm. All right, well, I hope that was helpful. Let's do another one. And then, again, let me make sure I don't read it out of the hard copy. Let me go to the book here. It says, or the PDF, it says, what is the force on a charge that is located at the 8 centimeter mark in the figure, given that Q is 1 microcoulomb? All right, so looks like they have a number line, and there is the 0 on the number line, and then 1, 2, 3 at the point 4. 3. 1, 2, 3, 4, 5. Okay, so at this point 3, there is a plus Q. Now remember, they just said Q is 1 microcoulomb. So that is one charge. Now it looks like, if we keep going at point 8, so 6, 7, 8, right here, there's a negative 2Q. So I guess that would be negative 2 microcoulombs. And then we got 9, and here's position 10. And then at position 11, there's just a single positive Q. And so that would be 1 microcoulombs there. So this is the part where it says here, what is the force located on this one? So this is the one at 8. What is the force on the charge located at x equal to 8 centimeters, given that Q is equal to 1.00 microcoulombs? So I'm going to take this like we did the others and say the electric field total then would be the electric field made by, and let me call this number 1, and this one over here number 2. So field created by number 1 plus field created by number 2. because the force on number 3, so right here, charge number 3, would be the value of the charge at number 3 times the field that's created by the other charges, which in this case is 1 and 2. So again, this gives me a chance to kind of solve a problem, not by looking at forces, but by looking at fields. So let me try and say, okay, what is the magnitude of field number 1? So field number 1 would be Coulomb's constant times 1 microcoulomb divided by the distance away, 1, 2, 3, 4, 5. And I believe 5 centimeters is in order. Yeah, because the number line, they say everything is measured in centimeters. Okay, so 1, 2, 3, 4, 5. Okay. So if I were to put in my numbers, and I'll do the numbers here. Let's start with Coulomb's constant, 9 times 10 to the 9th times 1 micro divided by 0.05 squared. And so number-wise, this is 3.60 times 10 to the 1, 2, 3, 4, 5, 6. And then looking at our units, remember this is a Newton and a meters squared over a coulombs squared. And this then is just a coulomb. So one of the coulombs downstairs, and then this would be in meters, so meters squared would cancel. And so we're left with newtons per coulomb, which is the units for the electric field. So again, that is the direction of the field from number 1 at point number 3. And since number 1 is a positive, I will then draw a green arrow representing electric field number 1 and saying, okay, it is pulling it, or sorry, not pulling it, this is just the field. The field doesn't push on anything yet. You got to put another charge there, but that would be one field. Now, going through the same logic for number 2, right here, I would say it's Coulomb's constant, and we are, again, same charge, 1 microcoulombs. But in this case, I think we're a little closer, because we're only at 11, and 1, 2, 3. So we are only 3 centimeters away. So putting in the numbers, 9 times 10 to the 9th times 1 micro divided by 0.03 squared would give me a field of 1, 2, 3, 4, 5, 6, 7. 1.00 times 10 to the 7th. And you can see that we've got the same units as we just did for the other field, so I'll just put the answer, now that we went through it, as newtons per coulomb. And again, notice that this would be pointing away from the positive charge, so it would be pointing to the left. So this one's actually in the negative direction. So to get what I will call the total field, I've got to combine these, keeping in mind their direction. So I've got 3.60 times 10 to the 6th newtons per coulomb. And I am then going to add it to the field for number 2, which I'm going to label as a negative direction. And so this would be 10 million, and this is 3.6 million. And so 3.6 million minus 10 million is a negative 6.4 million newtons per coulomb. So there's the electric field. Now, I'm not done, because remember, they did say, what is the electric force? So the force on number 3 is the charge at number 3 times the electric field that was just created by 1 and 2. So the charge here would be a negative 2 microcoulombs. Let me just double check that, yeah. And then times this electric field, which is negative 6.4 times 10 to the negative 6 newtons per coulomb. And so notice Coulomb's going to cancel off, and we're going to be left with a force in newtons. Now, also keep in mind, if I was drawing a net picture of the electric field, I'll come back here. The field from number 2, remember, is not only in the negative direction, but it's also bigger than number 1. So the total field after combining these two is in the negative direction, which, of course, that's why we put this negative 6.4, and that would be micro newtons per coulomb. But also keep in mind that the direction of the electric field is the direction a positive would go. And so this is saying that the total field is in the negative direction. But we're not putting a positive there. We're putting a negative. And so the field is the force is the opposite of the field. So the field is to the left, but the force is to the right. And again, I mentioned it a few times earlier, but that's what this math is saying when you write it as a vector. It is only in the same direction when you have positives. You put a negative there, and then the result, when you multiply the two together, is to get you a negative, and so the force ends up being negative. For a positive charge, it ends up being negative. And that's why then I put in a negative charge so that this goes then in the positive direction. Okay. Wait. Let me say that again. I think I said that backwards. So the field is in the negative direction. And so a positive would be in the negative direction. A negative would be in the positive direction for the force. And that's what I have here. Okay. I'm struggling on keeping track of these positives and negatives here. All right. So let me put, and I won't worry about the negatives. I'll just put 2 times 10 to the negative 6. And then 6.4 okay, and that was times 10 to the negative 6. I can't really read my own writing here. All right, so then I get a force of 1.28 times 10 to the minus 11 newtons. Okay. And that's really small, but I guess I'm kind of liking it. No. See? I keep messing up my sign. I'm sorry. I'm really keep messing up with this. Okay, so back here, I put a negative, but back here that should have been a positive. And that one should have been a positive. Okay, and so that positive and that one should just cancel, and we should have our 12.8. Okay, so 12.8 to the right. Yeah, how did I write that as a negative? Maybe, yeah. Okay, well, let me keep going here. I guess I tried to do too much today here, and my thoughts aren't as clear as they should be. My apologies. So hopefully this will still make sense to you guys. And then I think there was a part B to this one. Let me come back over here. Part B. A, given... Oh, B is for a different problem. I see. Okay, so and I'm not sure that would be that educational to see the same thing again here. So good. Let's move on. Let's see what else was next on this. 49. Okay, so let's try 49. That looked like another good one here. 49 says, find the electric field at the location of charge A as shown in the figure, giving that B is a plus 10 microcoulombs and C is a negative 5 microcoulombs. Okay. So they have Q sub A and Q sub B and Q sub C. And they say in the picture that these point charges are located on the corners of an equilateral side of an equilateral triangle of 25 centimeters. So my picture didn't come out quite as equilateral as I'd hoped. But that's supposed to be an equilateral triangle where the distance of each side, and I'll put it in meters, is 0.25 meters. Okay. And again, this being a more advanced problem, they're asking for the electric field here. Because then if you have that, you can just multiply by whatever charge you have at A and get the force. And that's why the field we kind of do first. And you saw that me doing that on some of the other ones here. And so the field is created by just the other two. We don't worry about the field right here. In fact, part B then does say find the force, now that I'm reading ahead here. So first it says find the electric field at the location of A. All right. Then they have said, given that B is a plus 10 microcoulombs and C is a negative 5 microcoulombs. Now, let me just kind of draw the field at point A from B. It would be pointing away. So I'm going to put a vector up at an angle. Whereas since C is a negative, it would be pointing towards it. And so what we've got to do is find the total of these two. And so this is where it gets real. This is where it gets hard. Let me start with this. Let me just start with what is the magnitude of the electric field from B? Because that is Coulomb's constant times the charge over R squared. And since we've done that a couple of times, let me do it kind of quickly here and say, okay, it is Coulomb's constant, and then times 10 to the negative 6, then divided by the distance separating them squared. And since I put everything in as coulombs or meters, we're going to get units of newtons per coulomb. 1, 2, 3, 4, 5, 6. And times 10 to the 6th. So that is the electric field magnitude at B. Now, magnitude at C is kind of the same thing. The only difference is I would have half the charge. So looking ahead and kind of anticipating that, why don't I just take that field and cut it in half? And so we're looking at a 7.20 times 10, and that should probably be a 5, right? 1, 2, 3, 4, 5 newtons per coulomb. So that could save you a little bit of work in these long problems by realizing that, hey, I'm doing the same calculation except I have half as much charge. And I should put magnitude of charge. Okay. So here's where it gets challenging, is these are vectors. And so like we did last semester, we need to look at the x and y component. And so what I need to do is to take what I would call the x component of B and add it to the x component of C. And then likewise, I need to take the y component of B and add it to the y component of C. Now, in order to do that, I need to probably come back here and do a little geometry and trigonometry. This equilateral triangle means this angle is 60 degrees, which alternate interior means that's 60, which also means that's 60 from, I guess, corresponding angles. And so looking over here at the x components of them, I would be taking cosine of 60, and both of them would be in the negative direction. So this would be negative 1.44 times 10 to the 6th cosine of 60. Add it to a negative 7.20 times 10 to the 5 cosine 60. And then I can combine all these together. And actually it wouldn't be too bad because cosine of 60 is 1/2, so that number actually becomes the same as that number, and then half of that again. And so maybe they set us up purposely with that. But I'm going to enter the full thing into my calculator because that'll help me on the y component. I won't bother to write the negatives into my calculator, but I will go 1.44 times 10 to the 6th times cosine of 60 degrees, and I better check the mode of my calculator. Okay, I'm in degrees. Okay, and then I will add that to 7.20 times 10 to the 5 times cosine of 60 and hit enter. So this would be 1.08 times 1, 2, 3, 4, 5, 6 times 10 to the 6th newtons per coulomb. So that'll be the negative direction. And the reason I thought it might be nice then to leave those into my calculator, because the y would look something like this. From B, it's pointing upward, so it would be a plus 1.44 times 10 to the 6th newtons per coulomb, and then sine of 60. But the y component for C would be angled down, so I'll put a negative 7.20 times 10 to the 5 sine of 60 degrees. So I think I warned you that, hey, some of these problems can be pretty hard and pretty long when we're dealing with all these components. All right, so if I take advantage of my calculator and just go re-enter and maybe scroll to the beginning so you can see it, there's the 1.44 times 10 to the 6th, and the only thing I want to change is a cosine to a sine. Now another thing I'd like to change is that to a negative, and then also the cosine into a sine. Now I'll hit enter. So this comes out to be 6.23 times 10 to the 1, 2, 3, 4, 5 newtons per coulomb. So kind of makes sense that the C, the upward part of, B, the upward part of B is a little stronger than the downward component of C. And so the net is up. And then, of course, both of these are negative direction, or to the left. So we got our two components. Now, let's go back here to the question. It says, find the electric field. We could actually leave it this way. This is called the components. This is the x and the y. Or we could say the magnitude of this electric field. And now we can take our x components and our y component and square them. So I could take this 1.08 times 10 to the 6th and square it, and add it to the 6.23 times 10 to the 5 and square it, hit enter, and take the square root. And if we wanted to know the magnitude, and I'm not sure how the author is really asking for it, 1, 2, 3, 4, 5, 6, but this would then be the magnitude. In fact, why don't I take a second to find the solution guide to this. Here it is, 49. Okay, let's go, 49. So he does put it together this way. Okay. So he does do the magnitude. And he also does the angle. So maybe I'll do that. And so noting that, and I'll just kind of draw what this would look like. This would look like a huge force or a field in the x direction and a little bit in the vertical. And so maybe we should then say, what's that angle? And I should just call it theta. But it looks like it's a perfect recipe for 30 degrees. So I think this is going to be the inverse tangent of, and I'll take the vertical component, 6.23 times 10 to the 5. Divided by, and I'll just do magnitude, 1.08 times 10 to the 6th. All right, so 6.23 times 10 to the 5 divided by 1.08 times 10 to the 6th, and inverse tangent, there's what I want, of the answer. Yeah, and 30 degrees. Okay, so 30 degrees. So there would be the answer to A. Fortunately, then, that makes B pretty easy because, as I was saying here, once you have the field, you just have to multiply by the charge that you're going to place there to get the force. And you could calculate it by magnitude, and then you can look at the direction, remembering that the direction of the force is the same direction as the field if it's positive, but it's opposite if it's negative. So as we just did for the direction is kind of, a little to the left and up at 30 degrees. And the charge we're putting here, the charge at A, and so let's go back to the textbook here. So A says, what is the force of A given that A is a positive 1.5 nanocoulombs? So the fact that it is positive tells me that the direction is that same 30 degrees upward from the negative x-axis. So it's kind of off in this direction. They're the same. The only other option was it would be opposite. So it would have been this direction had it been a negative that we placed here. But we're putting a positive 1.50 times 10 to the minus 9 coulombs there. So again, that makes the direction very easy at this point. It also makes the magnitude of the force very easy at this point. Because all we got to do is take our total field, 1.25 times 10 to the 6th, and multiply it by the charge, which is the 1.5 times 10 to the negative 9, and getting a force of 0.0 0, 0, 1, and I'll just call it 8, 8. And so that's both the magnitude and the direction. Okay, good. And so this was a long one, but it really hit home really well that what you need to do is figure out the field from the other two charges. Combine them together, and especially if they're not something real nice, you got to work out the x components and the y components. And then finally, from all that, you can finish it by just saying, okay, take that field and multiply by the charge. So the last step is pretty easy, but it's making sure you get the total field, especially if you have more than one charge there. And so you can see we're really getting to the hard ones now. All right, and so I have here number 61 also here on this list. Okay, so 61. Oh, and this one isn't quite so bad, but it's a throwback to Physics 121. And so, I mean, sorry, that's not your class. When you guys are 110. And so it's kind of a throwback to that one. And so here it says, looking at the figure, I should have printed the figure for you here on this one. But I'll just make a little positive and a little negative plate. It says, show that an electron passing between two charged metal plates that creates a 100 newtons per coulomb vertical field perpendicular to the electron's original horizontal motion. So the electron is shown coming in, so I'll put an E with a little minus. It has some speed V naught. The electric field would go from positive to negative, positive to negative, positive to negative, positive to negative, positive to negative. It would make a nice uniform field of 100 newtons per coulomb. So if we take a moment to calculate the force on this electron, we will first say, what direction is it? And so this will give me a chance to say the same thing again. That notice that you take the field and then you multiply by whatever charge you put there. And if the charge is a positive, then the direction of the force would be the same as the direction of the field. However, if this is a negative charge, which in our case it is, then the direction of the force is opposite to the field. And so this electron is going to be pulled upward. And so it's going to follow this path. And so the force is up. And the magnitude of that force would be the charge of the electron. That's the 1.602 times 10 to the minus 19 coulombs times the strength of that field. So 1.602 times 10 to the negative 19 times 100. And we are looking, oh, I guess I need a calculator for that one. But we are looking at 10 to the minus 17 newtons, so 1.602. So that's the magnitude of the force. And that's the part that is new. That's the part that is part of this semester. But what it does say here is that this is an integrated problem, so it takes you back to the projectile motion problems we did in Physics 110. And so they say if the electron has this initial speed of 3 times 10 to the 6 meters per second in the horizontal distance and is traveling in this uniform field for 4 centimeters, what is the vertical deflection? And so going way back, and I guess I'd say to chapter 2 even, we had a movement, we called it x, equals the initial position times the initial velocity, say in the y direction. So maybe we should call these y's, times time plus 1/2 times the acceleration in the y direction. And that's what I'm getting at here, is because what they say here is they want to know the deflection. So they want to know y minus y naught. So put the y's together, and they make it very clear that it comes in horizontally. So it has no initial velocity in the y direction. And so then we just have this 1/2 times the acceleration. And that would be the force in the y direction that we just solved divided by its mass. So we got to go back to Newton's second law and then multiplied by time. And we don't know time. So why don't I then divide my paper? This is the y motion, and this is the x. And I kind of did those backwards. But again, for projectile motion, we look at the two motions separately. And so then if I say x equals to x naught times initial x times t plus 1/2 acceleration in the x direction times squared, we can say the x minus the x naught, that's the 4 centimeters. And that has to equal the initial velocity in the x direction, which they say is 3 times 10 to the 6th meters per second multiplied by time. And there is no acceleration in the x direction because there is no force in the x direction. They made it very clear that the field is only in the y direction. And so that's why we came up with an acceleration in the y direction, but nothing in the x direction. So using that information, we can solve this for time. So we can go 0.04 divided by 3 times 10 to the 6th and get a short amount of time, because it's going really fast. It's not going very far, but 1.33 times 10 to the minus 8 seconds. So this is what I mean by it's a throwback to last semester. We had to do our projectile motion. We had to do the x and y separately. And so once we have that time, we can put it into this equation and answer what they want. How much is the deflection? Because there's the 1/2. The force we did a little earlier, so 1.602 times 10 to the minus 17 newtons. That's from up here. The mass, we'll go look it up for the electron. It's 9.11 times 10 to the minus 31. And then the time is 1.33 times 10 to the 8th seconds. And then we can square that. And so again, finally we can get what is the deflection. So I already have the time in my calculator, so I'm just going to hit square. And then multiply it by 1.602 times 10 to the negative 19. And divide that by 9.11 times 10 to the negative 31. And then finally, we'll multiply by 1/2. That's a 0.5. And hit enter. All right, so the deflection is not much. Kind of makes sense because it is not in there for very long. It's traveling so fast. But it does have some deflection. And so it's deflected just a hair upward. Okay. But here's where it gets more interesting. It's changed its projected angle. And so where it would have gone straight through, now it's got a small angle or maybe even a big angle upward. I don't know. But it could travel out and be hitting something much further from where it original was. So a small deflection early on right here can result in a big difference of where it would have gone otherwise. And I think that's where we're asked to do next, because B says, what is the vertical component? So final velocity in the y direction is equal to initial velocity in the y direction times acceleration in the y direction multiplied by time. Now, again, they made it very clear at the beginning that this electron only has a velocity in the horizontal direction. So that vertical piece is a 0. And then the acceleration is this same force, 1.602 times 10 to the minus 17 newtons, divided by that mass, 9.11 times 10 to the negative 31 kilograms. So there's the acceleration. And then again, the time is 1.33 times 10 to the negative 8 seconds. Okay. So this would be the velocity in the vertical direction. So 1.602 times 10 to the negative 17 divided by 9.11 times 10 to the negative 31 times 1.33 times 10 to the negative 8. And this has a speed of 2.34. 1, 2, 3, 4, 5 times 10 to the 5 meters per second. So I would call that a big speed, although in comparison to its 3 million, this is only roughly 10% of it. So it has some speed in the vertical direction, but only 10% compared to its horizontal. Which then brings me really to the main point. It says, what angle does it exit at? So it will still be traveling at 3 times 10 to the 6th meters per second in the horizontal direction. But it now has gained a 2.34 times 10 to the 5 meters per second in the vertical direction. And so there would be some angle here when they say, at what angle does it exit? And so that's the picture. And so I guess that angle would be the inverse tangent of the 2.34 times 10 to the 5 and divide it by 3 times 10 to the 6th. And let's see, I still got that number in my calculator, so let me just divide that by 3 times 10 to the 8th, and then let me take the inverse tangent of that. And so we're looking at about 4.5 degrees. And again, I would have expected a little bit more, but this was a pretty realistic problem of oscilloscopes and the engineering of them. So maybe, and that's about right in these tubes when we designed them in our engineering class. So, okay. So I'm going to go ahead and say that seems like a good answer, and won't even bother to kind of check the solution here, because my little supplement here is getting kind of long-winded, and maybe this is a good place to pause it. I did have 2 others from the harder book, and maybe I'll make a supplement to the supplement. But I'm going to stop this one here now. All right, take care.